goodness, there are a lot of questions sitting here in the chat. So a comment about the background. Power and internet are out in North Raleigh where I live, so I've actually had to come up to Northern White campus because I'm physically on campus and I need to keep the mask on while I do the live stream. So we're going to try to do our best to do this, but the only other option was not to hold live stream today. And based on the questions I'm seeing there, it's probably better I'm doing the live stream today. So I'm going to start with the emailed questions first, then I'll go to the chat questions, and then, yes, I saw the comment at the end. Please feel free to go ahead and ask the question. This should not take an hour to answer all the questions. So, first question I got, having difficulty determining the reaction mechanism. Feels like there are a lot of different things that point towards conflicting mechanisms that I find hard to choose. I'm also having some difficulty just going through the reactions in general. There's some problems in the homework that has to work through a reaction step by step, while sometimes I'm able to predict some products. I'm having trouble showing the electron movements and other specifics. So let's start with the big picture of determining going between SN1, SN2, E1, and E2. So substitution versus elimination. So not one or two, just substitution versus elimination. This is set by your reagents. So small molecules are typically going to do your substitutions. Big molecules are going to do your eliminations, assuming they are strong bases. And our ubiquitous strong bases here are going to be alkoxides, alcohols that have had their oxygen stripped off. Now when we go to alkynes, there are better bases than those. The thing about alkoxides is that the only thing they can do is get us down to an alkene. They're not acidic enough to bring us down to an alkyne, which is the last unit of material. So when it comes to elimination versus substitution, typically substitution, you're looking at small things like chlorides, bromides, iodines, hydroxides. Big bases, tert butoxide, isopropoxide, things that have like 20 or 30 atoms in the big bulky bases that have that big negative ion on them. Also, if you have anions, these are typically going to do elimination. So how do you know if it's the unimolecular or bimolecular mechanism? Well, there's three things you have to consider, and this is why you're going to see conflicting information, is that there is no universal truth. Now, on the test, it's going to be pretty black and white. Like, we're not going to give you like really ambiguous like ethoxide, propoxide, butoxide. Those are kind of debatable, but definitely something like tert butoxide versus chloride, you should be able to know that does substitution elimination. And the same thing is going to be true whether it's a unimolecular or bimolecular pathway. You're going to be given a list. And so what are the three factors that affect what type of mechanism you go through? The first one we're going to talk about is the nature of the carbon, and I don't like using this because it gets confusing. The truth is that all carbons, secondary, primary, secondary, or tertiary, will all go through some blend of SN1, SN2. They just have a better proclivity of doing one or the other, but the thing is that SN2 is inherently faster than SN1. And because SN1 is faster than SN2, and because SN1 is faster than SN2, even though SN2 may be like what most molecules are doing, they're doing it so slowly it looks like the SN1 product is dominating. But generally speaking, if we have a primary carbon, this is going to prefer the SN2 mechanism. And the reason being is that primary carbon cations are not very stable. So all things being equal, if we have a primary carbon, it's going to favor the SN1 mechanism. The tertiary carbons, carbons that have three things bound to them plus the leaving group, that's also going to prefer an SN1 mechanism because it's a very stable carbocation. Now, this kind of gets blurry when you get to secondary carbocations because they're kind of between the two. And so I would say in general from what I've seen, your secondary carbons prefer the carbocation mechanism, which is going to be your SN1 mechanism. Now, that said, it's going to be doing all three. Or it's going to be doing both. It's going to be doing both SN1 and SN2. So the two other things we do, which will basically push it towards a 1 or 2 mechanism, is one. The other is that we look at the leaving group. So things like halides. Halides really they're not very good anion, or they're not very good leaving groups. And the reason they're not very good leaving groups is because when they pop off, they have a negative charge and they leave behind a carbocation. So that positive negative attraction really drives them in. So typically if you're working with a secondary halide, it's going to still kind of want to go SN2. Whereas a tertiary alkyl halide, that's still going to want to do the SN1 pathway. And definitely if you have a primary alkyl halide, that's really going to want to do an SN2 pathway because you've got a primary carbocation, which isn't stable to begin with, next to a negatively charged halogen. So they're just going to pop right back together. It's basically trying to pull two magnets apart. The third effect is the solvent. And with the solvent, again, the exam's going to be pretty black and white about which solvent does which. But generally what we're talking about with solvents is how well does it stabilize the carbocation. So let's say we just have, let me go back to leaving groups. Sorry, not quite there yet. Alcohols prefer the SN1 pathway. So if we have a secondary alcohol, that's going to prefer SN1, whereas the secondary alkyl halide is going to prefer the SN2. The reason being is that when we pop an alcohol off, typically what we do is we protonate it first. And so when we protonate it, we form an OH2 plus group that pops off to form water, H2O neutral molecule, and the carbocation. The carbocation is positive, the water is neutral, and so there's really not that much of a driving force for them to come back together. So if you have a secondary alcohol, it's probably going to want to go through the SN1 pathway because the water forms a leaving group that really isn't attracted to that carbocation. And we can kind of see this with things like tolusyl chloride. Tolusyl chloride forms a very good leaving group, thionyl chloride, SOCl2. You form a very good leaving SO2 group. And because you have a good leaving group, you're going to favor the unimolecular, the SN1 pathways. Now, if you have a primary alcohol, this is kind of where we're going to see competing effects between SN1 and SN2, but definitely with a primary alcohol, you're going to see a lot more of that SN1 product. You're going to see a lot more of the rearrangement. So how does solvent affect us? Now I can talk about solvent. The way solvent affects us is that it stabilizes the carbocations. So if we just take the carbocations and put them in space, we have a primary, secondary, and tertiary. We know primary is more stable than secondary, secondary is more stable, or I'm sorry, primary is less stable than secondary, secondary is less stable than tertiary. Now what happens if we add a solvent? Well, if we add something that has a very low dielectric constant, like tetrahydrofuran, THF, this doesn't stabilize charges at all. And so we basically have a carbocation that just looks like a naked carbocation. There's nothing to kind of offset that charge and nothing to stabilize it. So if we have a secondary carbocation, it's not going to be very stable in a low dielectric constant solvent. Because of that, we typically will take typically when you take all three of these carbocations and you stick them in a nonpolar low dielectric constant solvent, it's going to drive it towards the SN2 pathway. Now, a mistake students make is they equate polar with dielectric constant. Polar is a spectrum, and things can be polar by definition only. Methylene chloride is a great example of this, CH2Cl2. You'd work with this in the lab, and it's the organic layer when you do the separatory funnels. So you get a water layer and you get a CH2Cl2 layer. Well, water's polar and methylene chloride's polar, but methylene chloride is polar by definition alone. It's so nonpolar it doesn't dissolve in water. And so methylene chloride will dissolve hexanes, and we know hexanes are nonpolar, so if we say like dissolves like, it doesn't make sense to say methylene chloride is polar, but it is by definition. So what we're looking for more is the dielectric constant, because the dielectric constant is going to give us a feel for how well it stabilizes charges. Now, if we take the same three carbocations and we put it in something like dimethyl sulfoxide, DMSO. DMSO is actually a better dielectric constant than water, and water is such a good dielectric constant that sodium chloride dissolves in it. So if you think about sodium chloride as positive ions and negative ions, they should be sticking together. It is so good at stabilizing those charges they can actually drift apart. So they're no longer held together by that positive negative charge. So when we go to a high dielectric constant, we end up stabilizing charges. And so something like DMSO will drive the SN1 pathway. So even though you have a tertiary, secondary, and primary, they become more stable under DMSO and they become less stable under THF. So those are your three effects. Primary, secondary, tertiary, leaving group, and the solvent effects. And again, it never proceeds purely from one pathway. So what it's asking you for is what's the dominant pathway. If you have a tertiary carbocation with an alcohol in it and a very high dielectric constant solvent, that's definitely going by the SN1 pathway. If you have a primary carbon with an alkyl group on it and tetrahydrofuran, that's definitely going by the SN2 pathway. The question is that if you just have a molecule, how do you drive it one way or the other? And the easiest thing you can do in that regard is the solvent. So that's why we put the emphasis on the solvent in this class, is that you don't always get a choice as to what type of group you're trying to substitute. So you don't always get a choice if it's a primary or secondary or tertiary, and you don't really get a choice on the leaving group because it depends on the molecule, but what you do get a choice on is in the solvent. And the solvent here is going to be what helps you drive it towards SN1 or towards SN2. So that's hopefully kind of helping you there with understanding what drives it. And if you take a look at the problems on the discussion board, I think it was last week, about SN1, SN2, E1, E2, and you see the two solvents, look at the two solvents and compare the dielectric constants. You should see that they're not anywhere close to each other. And from there, that will infer whether it's a unimolecular or bimolecular pathway. Choice of substitution versus elimination, that's not going to change with the reagent. The reagent sets whether it's substitution or elimination. Now, again, the full disqualifier out there to say like it's always going to be a blend. But definitely something like isopropoxide and tert butoxide, those are 100% going to do elimination. They do not like to do substitution because they're way too big. A small single ion sitting in space like chlorine and bromine, those are definitely going to want to do substitution because one, they're not basic at all, and two, they're just so small. They really can kind of get in there and react with the molecule. Now, in terms of the mechanisms themselves, and this is where I would recommend the book Pushing Electrons. There's a link to it in the initial course announcement, which is still up on the course website. We'll see how well I can get the camera, how well we can make this visible for you. So, wow, that's good. I have a sinking suspicion that these pens have not been used since spring 2008. Okay, there's hope for that one. Oh, thank goodness. Okay. So let's say L is our leaving group and X is the group that's coming in to do the reaction. And we'll break this into substitution and elimination. I'll try to bring the camera in closer. We'll see how well this works based on how I'm having to set this up. So with the substitution versus elimination, and we've got unimolecular mechanisms and the bimolecular mechanisms. So they always proceed the same way. If we have the unimolecular mechanism, we have our leaving group. The first thing we're going to do is we're going to draw an arrow from the bond to the leaving group. And when we draw an arrow from a bond to a leaving group, what we're doing is we're creating lone pairs. So first step in a unimolecular pathway is we form our carbocation, and we add a lone pair to our leaving group, and depending on what that leaving group is, will dictate if it has a charge. So if it's something like an alcohol, it'll pop off as an OH2, which is neutral. If it's an alkyl halide, that's an alkyl group that's leaving, that'll pop off as just an anion. The second step is that whatever our attacking group is, we'll draw bonds from the lone pair to the carbon, and this is where we get our CX bonds. If we have a bimolecular pathway, it all proceeds in a single step. So we draw a bond from the lone pairs to the carbon. This drawing lines an arrow from the lone pairs to another atom indicates that we're making a bond. Drawing an arrow from the bond to the leaving group, that will create lone pairs. We get XC plus L with lone pairs. Elimination is going to look really similar. We break the Cl bond. In this case, we're going to have two carbons. We break the leaving group, and then our group that abstracts uses this in lone pairs to break the CH bond, and we get the double bond. The bimolecular pathway, it's all what's considered concerted. So our attacking group hits the hydrogen, forms the carbon-carbon double bond, and we lose the leaving group. And this is why we memorize this class of reactions, is to say that, basically substitution versus elimination, E1, E2, these are all kind of following the same pattern. And that's why, again, this is kind of why we make you go through these mechanisms, is to understand that. All right, moving on to next email question. Can you go over the third problem on page 14? Now, just a fair warning, I updated the packets. There was a question that was off on one of these packets. So I'm on page 14. And the third problem for me is the primary alcohol. So this is, let's see here, 1, 2, 3, 4. This is the 2,3,4 trimethyl heptanol, 1-heptanol. So you got the alcohol. What you're going to do first is protonate that alcohol. You're going to get a positive carbocation on the primary. Now this is H plus in water. Water, definitely high dielectric constant solvent. You've got an alcohol, which is a fantastic leaving group, especially under acidic conditions. And so what's going to happen here, we're going to protonate the OH group. It's going to pop off of OH2. Because we've got a primary carbocation, we're going to get a hydride shift, and this is going to stick it on a tertiary, on that second carbon, which is a tertiary carbocation, and that's where you're going to get elimination. So the H plus H2O, this is code word for acid catalyzed dehydration of an alcohol. Acid catalyzed dehydrations are notorious for carbocation rearrangements, so you're going to get the carbocation rearrangement. Now, by Zaitse's rule, you're also going to get elimination on the most substituted carbon. So first thing we're going to do is protonate the alcohol. This is going to come off. Forming our primary carbocation. This carbocation is going to rearrange to give us the tertiary, and then elimination is going to be between it and the most substituted carbon. So we're going to get a double bond there when we finish with the elimination. And I'll bring it a little bit closer. I don't actually have a podium here to like post it on like I do at home. So again, we take our alcohol, we're going to protonate it. It's going to form off to give us a primary carbocation. That's going to shift to the tertiary. And then we do elimination of the most substituted carbon, which will give us this bond here. Now, if this isn't that problem for you, just go re-download the packets. There was one problem that had issues. It was showing the wrong substitutions. At least I think that's what it was. Yeah, we did need to update the packets. Okay, so that's it for email questions. All right, the lengthy chat. First question, how would you do the ionization on the spec 11? I don't understand how could you do it, and also do the second problem on 3-octanol versus octane. So honestly, just kind of think of it. There's two ways you can approach this. One is that you can draw out the molecule and count out the atomic weight. The second is let the name tip you off about what should be happening. So 1-octane versus octanol, or 3-octane versus 3-octanol. Octane is an 8-carbon chain molecule. It is C8H, 16 times 2, H18. So you can calculate the molecular weight for that. The 3-octanol just has an oxygen added between a carbon-hydrogen bond. So oxygen weighs 16. You're just going to take whatever the weight of C8H18 is and add 16 to that for the oxygen. And that's pretty much how all those problems work, is that there's nothing different in the molecules. The only thing we've done is that we've added an alcohol group, which adds 16 by the atomic weight, or we've added an alkyl halide, and what the halide does is it substitutes off a hydrogen. So hydrogen weighs 1, whatever your bromine weighs, I think 79.9, chlorine weighs 35.5. Basically, you're going to add the weight of the halogen and subtract off the weight of the hydrogen you substituted off. And that's how all those mass specs do, is that the heavier one is going to be the substituted alkane. So for 3-octanol versus octane, the 3-octanol is the one that weighs more. And if you look at the study guide, switch to desktop for you. If you look at this, come on, where are you? Huh, that's weird. I'm going to go with the one on the right as the octanol, just by sheer merit of the fact the spectrum's so compressed. There's probably some very little peak up here around 120. So I think it's more that you just need to make the picture really big to see what's going on. I think with that one, it's just more the resolution of the image. I mean, the other thing is just to compare the weight of the fragments. So mean, in general, what you're looking for is just the one that weighs more. And again, I would say because all these peaks look shifted up relative to this one, I would say this is probably the 3-octanol. The rest are probably a bit more obvious. Yeah, the chlorocyclopentane versus pentane. You can definitely see the spectral range is a lot bigger for the one on the left. So that's the chloromethane versus methane. Definitely different ranges. The 3-butanol versus the butane. The butanol has a bigger range. That's because it weighs more. And I'm guessing with the octanol, again, you can kind of look at the peaks on top of each other. Particularly when we start getting to 60, these start getting shifted further and further up. So I'm going to go with the second spectrum is probably the 3-octanol. But again, all you're looking for is heavier mass with these problems. Just say a reaction is SN1 and goes through the reaction. How would we state the stereochemistry if it is in plain straight line instead of a wedged or a dashed? Wow, that would actually be an incredibly hard problem to do. And so basically you would just redraw it. So you know you're creating a chiral center, and I'm assuming if you got like a wedge or a dashed, you can pretty much, I don't want to say this without coming out across too flippant. So let's say you've got a bromine, an ethyl group, and an isopropyl group. So here we got a chiral center, and I'm bringing it in a little closer for you to see. So this is what we have, and the question is, what happens when you substitute it off? Like, how do you draw? You go through an SN1 pathway, and you get carbocation. Let's say you sub it off with chloride. How do you draw it? Well, the answer is you can basically just take the other stereochemistry that's there and do the same thing. So we can do the Cl with the same stereochemistry, or we can do the Cl and we can change the wedges and the dashes on the ethyl and isopropyl group. So that's one easy way to do it, is that basically you take any stereo centers that are there and then just change them. Just do the wedge and the dash for both. So I would say that's the easiest, is that whatever wedges and dashes you have to represent that you went through an SN1 pathway, take your final structure, sub out your chlorine, and then just change the wedges and dashes so you got both conformations. One thing wedge, one thing's dash, and then just flip them in your second image. That's the easiest way to do it. How do you do alkoxide problems? Can you explain alkoxides? I don't get. So an alkoxide is what happens when you take an alcohol and you put it in the place of something like sodium, lithium, potassium, rubidium, cesium. So the column 1 metals like to take the protons off of alcohols and form basically the reaction you always get is ROH plus Na goes to H2 gas plus Na plus your RO minus. So this is RO minus is our alkoxide. Now, there are 3 different types of alkoxides. There's primary, secondary, and tertiary. So primary is where the alcohol started as a primary alcohol, so something like methanol, ethanol. Your secondaries are where the alcohol started out as a secondary alcohol, so something like isopropanol or 2-propanol or 2-butanol. And the third is where you have a tertiary alcohol. So your tertiary alcohol is tertiary butyl alcohol. That's an alcohol connected to a tertiary carbon. Now, primary alcohols can do elimination. They're also very good at substitution. And so when we start talking about, in the last test, about how to make ethers, we'll start doing Williamson ether synthesis and acid catalyzed ether synthesis, and we'll see that, yeah, it's pretty common that you can take primary alcohols and they'll do substitutions over eliminations. So when you make an alkoxide, if you want it to do elimination, you need a bigger, bulkier alcohol. So you want to go with secondary and preferably tertiary. And so this is why typically in the notes, what you're going to see is isopropoxide. So this is isopropanol, 2-propanol, turned into an alkoxide, or tert butoxide, which is tertiary butyl alcohol converted to an alkoxide. These are big. They do not like to do substitution. They much prefer to do elimination because of how basic they are. You cannot make these compounds stable in water. In fact, if you take isopropoxide and mix it with sodium, over time it will begin to pull water out of the air to replenish the alcohol. So something like sodium hydroxide, that's stable at room temperature, but isopropoxide and tert butoxide, if they're exposed to air and water at room temperature, they will decompose back into their parent alcohols to leave you behind with sodium hydroxide. So in terms of alkoxide problems, if it is isopropyl or tert butoxide, it is doing elimination. Now, the exception to this with secondary tertiary is what's considered intramolecular substitution. So this is the problem, the second last problem, where you take the alcohol, you've got an alcohol and a chloro group, and you react out the hydrogen, and that alcohol turns around and it attacks the chlorine to give you this ring. How do you know it's an exception? Well, the big thing here is if you can form a 5 or 6 membered ring. So if you can add sodium and you form an alkoxide with your molecule, and your molecule has a halogen on it, and if you make a ring by doing substitution, which in that case you end up with a 6-membered ring, so if you end up with a 5 or 6-member ring, that's most likely going to do substitution. It's going to make the rings because 5 and 6-member rings are just inherently more stable. The carbons are at the right angles. There's a lot of reasons for justifying rings. Generally speaking, though, if we have an alcohol with an alkyl halide on it, we expose it to sodium, that's going to do an intramolecular substitution. Otherwise, if you have primary alcohols, those are going to prefer substitutions. If you have a tertiary alcohol or a secondary alcohol that you convert it to an alkoxide, those are going to prefer to do elimination. What are the differences between carbon-13 and 1-HNMRs for alcohols and alkyl halides? So for alkyl halides, what the effect of a halogen does is it changes splitting for the J coupling because you're reducing the number of hydrogens. Your alkyl group, your halides, replace a hydrogen, so that is going to change your coupling. And it's going to downshift them. So your typical range for proton NMR for an alkane is 0 to 2. You can start getting into the 3-ish, 4-ish range when you start adding adding halogens to it because they're so electronegative. Carbon-13, basically all it does is it starts shifting it downfield. Your typical range for your alkanes, 0 to 50, 0 to 20. This is just going to send them further downfield. Proton NMR, alcohols are always a singlet. They produce a 1 proton signal for each alcohol, and it's always a singlet. And the reason is that alcohols undergo hydrogen bonding, and because in order to undergo hydrogen bonding, they basically have to exchange protons with each other, and they do that through the alcohol hydrogens. Because they are busy being exchanged, they do not have time to J couple. So the J coupling goes on slower than the hydrogen exchanges. Because of this, they cannot ever J couple within the NMR. So what you're going to see for alcohol NMR is you're always going to have a singlet with area of 1 for that alcohol, usually downfield about, I think it's 5. Now for carbon-13, what your alcohol does is it's like any electronegative element bound to carbon, it's going to start sending it downfield. Can you come up with a few additional practice problems for the reactions for us to do? I need to practice to get on it. I would recommend the homework. I can't come up with any off the top of my head. That's what the packets are for. So the other option, the textbook, there are free textbooks. So you have the Connect software that you paid for. That textbook's going to have textbook problems. Also, if you go to the course announcement, there are links to other free textbooks. You can do the problems in those as well, and those problems should have solution sets with them. Do we need to know the functional naming of alcohols and alkyl halides? I only get to do the substituted version of it. Honestly, both are correct. So I use the alcohols interchangeably depending on what I'm working with. Simple alcohols, I think use the whatever one is like the something alcohol. So like isopropanol, ethyl alcohol, isopropyl alcohol. Those common solvents are typically about the only ones where you see that type of naming. Whereas the 1 propanol, 2 propanol, 1 ethanol, that's going to show up a lot more when we start substituting things on it. So I think that's the functional one. The functional one is a lot more useful when you start putting functional groups on it. That's why we call it the functional naming system. But again, if you write both, you're still correct. There's nothing wrong. IUPAC doesn't pick one over the other. The reason why we have the substitutive is that it's just a lot easier. The reason why we have the one that's like ethyl alcohol or methyl alcohol is one, those are the historic names for them. So we didn't want to completely rename these things for the sake of IUPAC, so they just kind of got wrapped in. And the second is that they're just very simple, like one ethanol or one propanol versus two propanol versus isopropyl alcohol. Like some of these can get really complicated, so you can kind of see, oh, I know. So like terp-butanol, that is technically IUPAC, but the one where you number it, the 1-methyl or 2-methyl 2-propanol, that's harder to say out loud, so we just call it terp-butyl alcohol. But again, if you name by either, you're correct. Like, I'm not going to require you to do one or the other, but you're definitely going to find the one where you have to number the positions of the alcohol. That's a lot more useful, particularly when we start adding more functional groups to the molecule. Does tolusyl chloride go through SN2, which the reactions we had to memorize don't go through SN2? So tolusyl chloride is actually debated. So I'll give you the full disclosure there is that tolusyl chloride, people debate if it's an SN1 or SN2 pathway. Generally speaking, it is considered an SN2 pathway. It acts like an SN2 pathway a lot. That's it. It does occasionally do an SN1 pathway. But the reason why we work with tolusyl chloride is that it forms a good leaving group with alcohols. And because it is a good leaving group, occasionally it will just pop off and we get that SN1 pathway. But the thing is that the SN1 pathway creates two products. One of them looks like the SN2. Generally speaking, when we measure it, we get the SN2 pathway. So which of the reactions we had to memorize don't go through SN2. Any type of simple substitutions like sodium chloride, sodium bromine, anything where you've got like the ion doing substitution, those are typically not SN2. The way we force SN2 with things like that is with the solvent, and if we're lucky, we're working with some type of ion. We're working with some type of alkyl halide or alcohol that prefers the SN2 pathway. But the reason why we have things like phosphorus tribromide, PBr3, SOCl2 is because they are stereoselective. If POCl3 is creating double bond, then does it go through E2? Yes, and that's why we like POCl3 is that it does guarantee an E2 elimination, gives us a lot of control over the cis-trans products. It's synthetically useful in that regard. One thing I'm not going to assess you on is really like giving you examples where because there are definitely situations you can create where POCl3 does not react because it doesn't have a hydrogen in the correct position to do E2. I think those are interesting reactions. I think they're also kind of esoteric, so there's no point testing on them. But do be aware of that yes, POCl3 like SOCl, so the reason why we do SOCl2, thionyl chloride, it goes through an SN2. The reason why we do tolusyl chloride, it goes through an SN2. Your E2 equivalent to this is POCl3. If you want to guarantee that you're going through an E2 mechanism, you work with POCl3. But like thionyl chloride and tolusyl chloride, same drawbacks. Those are all air and water sensitive compounds. So if you want to guarantee this mechanism is going to be an SN2 pathway, the trade-off is you're doing this all in an argon environment. Third problem on simple reactions. Alcohols and alkyl halides on study packet go through SN1 and doesn't create a what is quiche wedges and dashes. So again, go check to make sure you're not working with an old version of this packet. It did get updated because there were a couple that were problematic. We make these ourselves, so yeah, we do kind of have to do our own quality control. But let's see here, simple reactions of alcohols and alkyl halides, and no, it wouldn't surprise me if the audio is not picking up really well in this room. I can drag up the gain. On my end, it's showing that it's actually kind of like redlining in terms of what it's picking up, though. Third problem, simple reactions. So this is the so HCl has the OH. If you add the H plus to it, you're going to get, oh, why does it show? Look it up. It shows it. It shouldn't. That's not a chiral center, so I would just say that's just kind of a mistake in the key. But you wouldn't be wrong if you wrote both. It's just that there's no point in writing both. I don't understand reactions. Can we go over it? There are gaps in my understanding, and I'm panicking. how would you do the discussion board this week? So as far as reactions go, I don't really know how to answer your question. So you've got the notes go through, the PowerPoints go through the different reagents, what they do, what you need to know about in terms of their stereospecificity. You've got the packets that kind of like assess that, and then you've got the homework problems that assess it well. The discussion board this week. I like this question a lot. It will definitely test to see how many people are just kind of plugging and chugging and how many people are really thinking about it. So we have HCl and we've got 3 products, product 1, product 2, product 3, and it tells you that one product is elimination, the other 2 are substitutions. And I really like this because, so this is an acid catalyzed reaction. We have HCl. And there's a couple of things that can go on here. Is that one, we can protonate the alcohol and we can do elimination. So that's your elimination product, is you form the 1-methyl cyclohexene. Now, for the substitution, there are 2 pathways. There is SN1 and SN2. And so what I see a lot of students try to do with this discussion board is they try to give me substituting the alcohol, the OH with the Cl, and they give me both the wedge and the dash. And that shows that you really don't understand the mechanism. So let's consider the 2 pathways, SN1 versus SN2. So if I do the SN2 pathway with the chloride, and bring it up a little bit closer for you to see it. Let's say I do the SN2 pathway with the chloride. Well, what do you know about SN2? Well, SN2 always does stereo inversion. So what I will get with this is the trans methyl chloro complex. So it's 1 chloro, it's trans, 1 chloro, 1 methyl. Or trans 1 chloro, 2 methyl. Oh, this laptop's being stubborn. So that's your SN2 pathway there, is that you, oh, come on. Is that you're subbing out the hydroxide through the chloride to give you the trans complex. So that's SN1. What about SN2? Or sorry, that's SN2. What about SN1? And this is where students get that knee-jerk reaction of, oh, I'll just flip the inversion. I'll just change the stereochemistry. That doesn't make any sense whatsoever. So if I do the SN1 pathway, I have to proceed through a carbocation intermediate. Well, am I going to see a hydride shift? And so if you're seeing it, the SN1 mechanism produces a carbocation. And if we can rearrange, we do. And so what we do is we rearrange this carbocation and we create a tertiary carbocation in its place. Now the chlorine is going to attract the tertiary carbocation, and we're going to end up with this achiral molecule. So if we go through the SN1 pathway, we only have 1 product, and that's the 1 chloro, 1 methyl group, because we're going to get carbocation rearrangement. So your only option, your 3 products here are 1, the elimination to give you the 1 methyl cyclohexene, the SN2 product, which is the trans chloromethyl group, trans methyl chloro product, and then the SN1 product, which is the 1 methyl 1 chloro. And that's the discussion board. Those are your 3 products. But again, what I see a lot of students trying to do is they try to say, oh, it's both the wedge and the dash for the chloride with the 1 chloro 2 methyl product. It's like, you can't produce the cis chloromethyl group, cis chloromethyl product by any of the mechanisms. And the reason you can't do it is that in order to get that inversion, you'd have to go through a carbocation, and if you go through a carbocation, you're going to get the rearrangement that's here behind me. If a solvent is polar product with a low dielectric constant, would it favor one of mechanisms? So Generally speaking, it can't be protic if it has a low dielectric constant. It can be polar by definition, but it can't be protic, and the reason it can't be protic is that that protic comes from a very strong disparity between the oxygen-hydrogen bond. But that said, if it's a low dielectric constant, you're typically favoring the bimolecular pathway, the two mechanism. So that's it for the questions I've been emailed. That's it for the questions in the chat. Again, concerning the volume issues, like you can kind of see it on my end that it's redlining down here, so I'm not quite sure what's going on the other side of this, but I've got the volume jacked up about as high as I can safely go with this microphone. So, and at least it is picking up stuff this time, right? So are there any questions there in the chat? Again, I don't like having to do the live stream like this, but I am sitting on North Campus right now because I didn't have internet at home. Yes. So the thing about protic is that the protic basically occupies our base. Usually our nucleophile has a lone pair that likes to attack positive things, and so by having a proton in the solution, it kind of busies our nucleophile so the carbocation has time to form. That said, dielectric constant is the easiest thing to look at. If it's less than 10, you're probably looking at a bimolecular pathway. Definitely, if you're starting to get above 40, you're probably looking at the unimolecular pathway. And again, the whole video from the start, like there are little nuances, and this is why you'll start seeing a lot of videos contradict each other, is that it depends. And I hate giving you that answer, but it depends. The world is a very gray area. We definitely run a reaction in Orgo 2 that should be by a unimolecular pathway, and it acts very much by a bimolecular pathway. And it's simply because the conditions that, like, we just happen to be like hitting the right molecule that prefers to go through the bimolecular pathway over the unimolecular pathway. It's weird, but it's how it works. How do you identify the subshells from orbital wave function graphs? So the subshell. So I think what you're referring to is it S, P, D, or F? So you have big N, which is the principal, or little n, which is the principal quantum number. That's the one that sets the number of radial nodes. It also sets the row on the periodic table. With that, you have the angular momentum, and so the angular momentum will sit back and tell you whether or not you've got an S, P, D, or F orbital. Now, the thing about the angular momentum, you're welcome. So the thing about the orbital angular momentum is that it describes the number of planar nodes. So that quantum number L tells you how many planar nodes. So if you see a shape that clearly is just a sphere, this is an L equals 0, that's an S orbital. And the way I remember S is that they're just spheres, and it's the only one where the letter actually kind of makes sense. The next one up is where you have L equals 1, and this is where you have one plane. So if you look at the orbitals, what you're going to see is it looks like the orbital has two symmetric sides to it, and these are your p orbitals. So your p orbitals look like teardrops that are touching end to end. There's an X, there's a Y, and there's a Z. And so those are your p orbitals. Your d orbitals have two planes, and so you're going to see basically 4 regions in the graph. And 4 of the 5 d orbitals look like 4 teardrops that are touching at x, y, z equals 0. And they're just oriented differently along space. So pxy, pxz, pyz, and px squared minus y squared, they're all along different axes. The only one that looks kind of weird, it looks like a p orbital, so it's got the teardrop and then it's got a ring in it. There's actually 2 planes of symmetry there as well. It's a lot harder to see. Then you get to L equals 3, these are F orbitals. F orbitals have 3 planes of symmetry, and what you're going to see is it looks like 8 teardrops. So yeah, 8 teardrops, 2 above and below a given plane. They're going to basically look like d orbitals if you double them up and stack them on top of each other. Most people don't even try to bother drawing the F orbitals, so if you see something super complicated with 8 lobes, it's definitely an F orbital. But that's how we identify the different suborbitals. We go through and we see basically the number of planes. These are nodal planes in the angular momentum. If we don't see any, if it's a sphere, it's an S. If we see one, those are the teardrops, those are P. If we see 4 teardrops, that's D. If we see 8 teardrops, that's F. Psi and psi squared. So if you're going off of so for the psi and the psi squared, the only ways I've ever seen those are presented are for the principal quantum number n. So n describes the number of radial nodes, and the psi squared is the probability density. So if you see just a continuous function, it'll look not log normal. It's kind of all crunched up towards the front. If you only see one curve, that's n equals 1. If you see a little dip at the front and then you see the normal curve, that's n equals 2. If you see 2 dips, n equals 3, 4 dips, n equals 4. So it's always the number of little small humps you see at the front minus 1. That will tell you, or plus 1, that will tell you which principal quantum number you're in. Look in the chart for dielectric constant. It says acetic acid has dielectric constant 6.2. It's polar product. So would that favor one mechanism? Yes, I would say. Well, I'm sorry. Would it favor one? I would say it actually would favor probably a 2. Just because of how low the dielectric constant is there. So yeah, even with acetic acid, I don't think that number is right. Actually, I really should go back, look it back up and see, because that seems really low for acetic acid. It's kind of sitting on my to-do list. .15, that's so weird that it's so low. But apparently it's just lousy at stabilizing charges. I would still say it favors the bimolecular pathway, even though it's polar, even though it's protic. It's just lousy at stabilizing charges. And again, this is why polarity is not such a good thing to go by. Like the dielectric constant is a physical constant. You can measure it. It does have an actual derivation for where it comes from. So it may seem weird that it's low, but you can probably, there probably is a good reason why it's as low as it is. Acetic acid may just simply not have the ability to stabilize charges because of how small the molecule is and how basically compressed the charge is around it. Like it may not, it may just be because of those two options, it just looks like a big ball of negative. And so typically what happens with dielectric constants, the reason why they get so large is because there's clearly a positive and negative end of the molecule, and it may just be with acetic acid because you've got this big carboxylic acid group paired with a little methyl group. It just looks like one big ball of negative, and all that positive that you would expect to see for the other end of the charge, the other end of the magnet, basically the oxygens of the negative end of the magnet, the methyl group's the positive end, it's all wrapped up in that negative charge. So it's like if you look at trifluoromethane, CF4, carbon-fluorine bonds are super polar. So if you look at between the carbon and the fluorine, yeah, there's a big charge difference between them. The carbon is very positive and the fluorine is very negative. But with CF4, all the fluorine is on the outside, so it looks like just a big ball of negative. There is a positive and negative in the molecule, but the positive end is within the molecule itself, so it's effectively not there. And I assume with acetic acid, it's probably the same way, is that because of how small that molecule is and how big the carboxylic acid portion of it is, it probably, you just don't see the positive end of the molecule. Yes, water is a good baseline. We know water prefers the unimolecular pathway. And so if you're seeing numbers like water, it's probably SN1, E1. If you're seeing numbers like THF, hexanes are a good one. We know hexanes have no ability to stabilize charges. If it's down there with hexanes, it is probably a biomolecular mechanism. Again, with all those caveats from the beginning of the live stream. I would say when you start getting to acetone, this is when you need to start looking at what you're working with. So if you're working with a primary carbon, it's probably still going to want to do the biomolecular pathway, the SN2, but definitely the secondary is going to start moving more towards SN1, and tertiary is definitely going to do the SN1 pathway. But you can't really like split hairs with this. You can't really like sit back and say, well, with this particular dielectric constant, it all goes this way or that way. The extremes are easy to see, but the kind of gray areas, like when you start getting to something like acetone, like you'll see the effect more on secondary carbons, but on primaries, they're probably still going to want to do the SN2 pathway because you really have to stabilize a primary carbocation. And if you don't have an alcohol as your leaving group, you're probably definitely going to have an SN2 pathway, even with a dielectric constant of 20.6. So it's very contextual. It's a lot of things that go into this. You're welcome. You're welcome. So you got another 6 minutes left. Oh, McGraw-Hill is awful software, but like it's what we have. We've talked to NC State, and they use Achieve software. Didn't do any good this semester, but we are looking to possibly look at other software. We had to agree with their statement. Students don't really read the books; they use the PowerPoints, and really the book you're supplying. The best book is the book that has the most problems and the most solutions in it, so they have more practice. With hopefully the implying assumption that the book's solutions are actually correct. But Connect is what we've historically used. I've only been teaching this course for 2 years now, and like we're finally to a point where like maybe we should start looking into alternatives to what we're doing. But even on my end, like it's weird that I'll add problems and suddenly like a year later I'm looking at the problems like, oh, why did I ever add this question? It's like I don't think I did. I think they changed the question pools. I didn't tell anyone. See, I'm not a huge fan of Connect, but I will also concede there's not much else out there to work with. I'll just say on the instructor end, it's not the best software in the world. But again, I've worked with Webassign. Webassign has its own set of issues that you have to program your own questions. If you really want questions that don't disappear if you change the books, they change book editions, and then it's all HTML programming, so you don't really see the questions when you're writing them. What you see is a lot of HTML code. My freshman year at college, we learned how to program in HTML as an intro to a computing course. So, like, honestly, it's not as bad as it sounds. But you begin to understand, like, why. Yeah, you start beginning to understand why software got developed to help with HTML programming. All right, so that's it for today. Organic folks, do remember that you've got your exam tomorrow. So regardless of A, B schedule, you are showing up. Email should have gone out today. I set the announcements. What room you're in, I'll put the note on the door, lab door as well, just so if you do show up, you will know that you need to go to a certain room. And I will see a lot of you tomorrow.